Definition. A random variable, for example denoted with the capital letter X or Y, is a function, and it assigns a real number to each point in the sample space S. This is best understood with a simple example. Let's suppose I toss a coin 3 times. My sample space consists of 8 points that look like HHH or THH or HTH that represent whether we obtained heads on the first, second, and third tosses. Suppose I'm interested in a random variable which counts the number of heads. Call it the random variable X. The range of values of X, in this case, is the set of integers 0, 1, 2, 3. Only these values are possible for the random variable X. X is a function on the sample space. If you give me a specific point, for example HHT in the sample space, then X assigns to that point the value 2. It counts how many heads in that sequence. X of HTT is 1, and so on. X is defined for every point in S. To every point in the sample space, there corresponds a real numbered value, X of S. But it need not be unique. For example, the second point, THH, and the third point, HTH, all have the same value for X. X of THH is 2. X of HTH is also 2. The model for random variables is a rather clever device designed to explain why it is that when I repeat the same experiment twice, for example, I throw a die and observe a number, I toss a coin, or I measure the return on a given stock, I end up with different values each time. The idea behind this model is that somewhere a random experiment is conducted, probably in a place in the universe hidden away from you, possibly with many invisible factors influencing the outcome. In some giant sample space, a point, A sub I, is randomly generated. You may see neither the sample space nor the point that was generated. Instead, you see the value of some real-valued function, x of ai, where x is a function that assigns to all the outcomes in S some real number. The random experiment which generates the return on a given stock is an extraordinarily complicated experiment, influenced by all the traders and economies in the world. But at the end of the day, you see a return of 0.3%, the value of some function on that sample space. Describing events using random variables. When we wish to refer to the set of points in the sample space for which x of s takes the value 2, rather than write it in the rather clumsy set-theoretic notation, by tradition, probabilists simply write square brackets x equals 2. You can take this to be a subset of the sample space, in other words, an event. And when we wish to determine the probability of this event, we'll write the probability, in brackets, x equals 2. Definition. Discrete random variables. A random variable, which takes a finite or countably infinite number of distinct values, the range of x is countable, is referred to as a discrete random variable. So a discrete random variable can take values like 0, 1, 2, 3, the positive or non-negative integers. It could take a finite subset of these. It could take values like 1/2, 3/4, 1/4, any finite subset, or a subset which is countable in the sense that it can be put in one-to-one correspondence with the positive integers. Later on, we'll discuss continuous random variables. These are random variables which can take any value in a non-degenerate interval. For example, a random variable which can take any number in the interval between 0 and 1. In this case, the range of the random variable is not a countable set. There are many simple examples of discrete random variables. Things like the number of students in a class in a given day, the number of travelers in an airport lounge, the distance between two randomly chosen locations, if we round distance to the number of kilometers or miles, and time rounded to the nearest second, or height, again, rounded to the nearest millimeter. These are examples of random variables with a countable number of possible values, or a finite number. By contrast, continuous random variables include things like your weight. Your exact weight, presumably, is some real number, not necessarily a rational number, not necessarily rounded off, but a real number that could fall in an interval between 0 kilograms and 500 kilograms. Similarly, the exact distance between two randomly selected places or points is a continuous random variable. It can take on any real numbered value in an interval. Time, exact time, is a continuous random variable, as is your precise height. Let's return now to discrete random variables and define a probability function. A probability function is a device for describing the probabilities associated with a discrete random variable. It's a function. We'll usually refer to it as little f of x, and little f of x is the probability that capital X equals little x. It tells us the probability of each value little x, and it's a function defined over the set of all possible values of the random variable x. So it's not a single number. It's a function on the range of the random variable capital X. A probability function has two very important properties. First, it represents a probability, and probabilities are all non-negative, and so f of x is greater than or equal to 0 for all values of little x. Second, when we add over all possible values of a random variable, the sum of the probabilities should be 1. So the sum over all values of x, f of x, is equal to 1. Example. Suppose we toss a fair coin 10 times and count the number of heads occurring. This is a random variable which takes possible values 0, 1, 2, 3, up to 10. Let's determine the probability function for that random variable x. Start by determining, for example, the probability of a sequence that starts with 5 heads in a row and ends with 5 tails. That's just one of many sequences which lead to the event x equals 5. And since we've specified exactly what happens on each one of the 10 tosses, the probability of that particular point is 1 over 2 to the power 10. But how many such sequences are there that have exactly 5 h's and 5 t's in them? We're looking at sequences of 10 letters, 5 h's, 5 t's. How many ways can we permute those letters? It's simply the number of times we can pick locations for those 5 h's. 10, choose 5. And in general, if I had a total of x heads, h's, in a sequence, there would be 10 choose x such sequences. The probability that capital X equals little x, the probability function for the random variable x, is 10 choose x times 1 over 2 to the power 10. Of course, we should begin by checking to make sure that is a probability function. Certainly every value of f of x is non-negative, and we'll have to check that the sum of f of x over x from 0 to 10 is equal to 1 in order to verify that it's a legitimate probability function. Although it may look like a somewhat complicated function, if we plot the values of f of x, as we've done in the histogram at the bottom, as x goes from 0 up to 10, you'll notice that the most likely value is in the middle, and the values are decreasing as we approach either of the two ends, 0 or 10. Question. For what constant value k is f of x a probability function, where f of x equals k times x? Certainly the values of f of x in this case are greater than or equal to 0, so we only need to check under what conditions the sum of f of x is equal to 1. That is, the sum of k times x goes from 1 up to 10, is equal to 1. We can factor out the k, and we're left with k times the sum x goes from 1 up to 10 of x, and that becomes k times 10 times 11 over 2. K times 55 equals 1. And so the solution to this is k is equal to 1 over 55.